everyone, and welcome to Thermochemistry. So by now, we learned about thermal images and thermography, and now we're going to learn about the energy in chemical bonds. So the question of the day is still, why do you get hot when you exercise? I want you to think about that question as we go through the PowerPoint. So we're going to learn about thermochemistry. I want you to think of the word thermo. Think of words like thermometer. What do you think thermo means? Hint, look at the pictures. So thermochemistry is the study of heat released or required by chemical reactions. Fuel is burnt to produce energy. Combustion, which you know as one of the 5 basic types of chemical reactions, is when fossil fuels are burned, or combustion is when a hydrocarbon and oxygen gas reacts to form carbon dioxide and water. All combustion reactions release heat. And that makes sense. When you burn something, heat is released. So when we talk about reactions, we're actually talking about collisions. Can you think of a collision? Like cars crashing, or if you're, chasing around your little brothers and sisters and you bump into them. So collisions. Reactions happen when bonds are broken and the atoms of the reactants are rearranged. Collision theory states that bonds are broken and or formed when reactant particles collide with enough energy and with the correct orientation. An activated complex is an unstable cluster of atoms that exists during the transition from reactants to products. So things have to collide for a reaction to take place. If the molecules or the atoms aren't next to each other, a reaction will not take place. So let's look at a reaction. So particles must collide and they must have the correct orientation. So an example, the first example, we have a fruitful collision, which means it's going to work. As we see, molecule AA is going to react with molecule BB. In this reaction, there is enough energy and the orientation of the molecules is correct so that we can form a new product. We're going to form one molecule of AB and another molecule of AB. Now, do you see the orientation? A is AA where they're on top of each other, and BB is where they're on top of each other. So when they collide, A is going to be next to B. But now let's look at the second example. Do you see when molecules AA and BB collide? A and B are not together this time. Do you see that? Their orientation is horizontal. And that's just not going to work. So they're not going to form an activated complex, and they're not going to be able to form any new product. So when the reactants have enough energy and collide with the correct orientation, the reaction is successful. However, if the reactants do not have enough energy, or their orientation during the collision is incorrect, then the reaction will not be successful. There's 2 ways to have an ineffective collision. Either they're not orientated correctly or there's not enough energy. It has to stick. You need energy. You need energy to break bonds. So if we look before a collision, in this example, we're going to use some real molecules. So before a collision, we are going to have a chlorine molecule is going to collide with this chlorine nitrogen oxygen molecule. Now, chlorine likes to be next to chlorine, right? It's the Brinkelhoff twin, so it's totally cool with that. So they're orientated correctly, and chlorine will find a nice, stable molecular molecule. So they form, it's an effective collision. And this chlorine is going to break off the nitrogen, and we're going to form chlorine gas and nitrogen monoxide gas. It's an effective collision. But now we're going to rotate that molecule, the oxygen, nitrogen, chlorine molecule. Now, do you see that chlorine is now going to collide with oxygen? Well, that's not going to work because oxygen has 6 valence electrons and chlorine has 7. So there isn't really a way for them to each have 8. They don't want to be together. They don't work. Doesn't work. So it's an ineffective collision, and we're not going to have an activated complex. So like bumper cars, that chlorine is just going to go in the opposite direction. And since the molecules are always moving, well, here now, that chlorine might hit another chlorine, and then we'll have an activated complex, and we'll have a new product taking place. Okay, the next thing we need to talk about is systems and surroundings. So there's 2 really big parts to a chemical reaction. There's the system, which is a part of the universe which your focus is on. So it's what we're talking about. It's the molecules that are colliding. And then we have the surroundings. It's everything else in the universe that we're not focusing on. Energy that moves from one object to another due to temperature difference is heat. The transfer of energy happens through collisions, with heat always flowing from hot objects to cold objects. But we're going to talk about heat exchange. So in this case, if the blue liquid inside the beaker is hot, it's going to flow from the system, which is our beaker, and our solution to the surroundings. And over time, our solution is going to cool down, and our surroundings are going to heat up a little bit. So during any chemical or physical process, the energy of the universe remains the same. Can't change the universe. If the energy of a system increases, then that energy must have come from the surroundings. Heat is the transfer of thermal energy from one object to another due to temperature change. Now, temperature is an indirect measurement of the thermal or heat energy. Temperature is also how fast the particles are moving. It's their average kinetic temperature, or their average kinetic energy. So the faster particles are moving, the higher the temperature, and the stronger the collision energy we're going to have. But temperature is not thermal energy. So if we look at the coffee cup, it has a greater temperature. It's 90 degrees Celsius. However, if we look at this bathtub, it has greater thermal energy because there's more liquid. There's more, so we're going to have more of this heat being transferred from the liquid water in the bathtub to the surrounding bathroom air, or the universe. So there's 2 different ways to look at how heat is transferred. We have something called exothermic and endothermic. Let's think of the word exo for a second. Let's think of words that have the prefix X, like exit or exoskeleton on a beetle. What do you think X means? X means the outside or the surroundings. So in an exothermic process or chemical reaction, it's any process that gives off heat. It transfers the thermal energy from the system to the surroundings. So we can think of it as the heat exiting. And exothermic reactions feel hot because that heat is exiting the system and going to the surroundings. Endothermic reactions, those are different. In an endothermic process, it's the opposite. It's any process in which heat has to be supplied to the system from the surroundings. So endothermic processes feel cold to the touch. In an endothermic reaction, you have to add energy into the system. You're adding, the heat is transferring from the surroundings into the system. We can look at two different reactions here. So up above, we have 2 moles of hydrogen gas react with 1 mole of oxygen gas to form 2 moles of water. We're just making water here. And this is the exothermic reaction. It's going to feel hot. We're going from gas to a liquid. We're going from gas to a liquid. And that is going to be hot, okay? In a different reaction, we have to supply energy to a system. So if we're going to go from solid water, which is ice, to liquid water, we have to add energy. You have to raise the temperature. You have to make those collisions more intense. Those collisions have to be energetic. So you're adding energy to the system. You're speeding up those particles. And that is overcoming the intermolecular forces, which is melting. So endothermic reactions feel cold to the touch. We also have another one where we have mercury oxide is going to decompose, so a decomposition reaction, to form 2 moles of mercury metal, that's liquid, and 2 moles of oxygen gas. So this reaction is going to feel cooler once it's over, but it takes energy to break those bonds to make this reaction go. We can think of things that you know of in everyday life. Burning fuels, like in a car. You put gas in your car, you turn on the engine. It's an exothermic reaction. Have you felt the hood of a car? It's hot. Yeah, that's an exothermic reaction right there. It's a hot reaction. We can also think of something that's endothermic, that feels cool. Photosynthesis. Have you ever walked on a lawn in the summer? It's a lot cooler than walking on the sidewalk, I'll tell you what. That's because photosynthesis is an endothermic reaction. The sun is the energy source. It supplies light, the photons, right? The light waves, they go into the plant and they're going to turn the carbon dioxide plus water is going to end up making a carbohydrate, glucose if you will, and oxygen gas. It's photosynthesis. It's the opposite of combustion, right? And that process feels cool, which is why the blades of grass that you walk on in the summer don't burn your feet, but the sidewalk will. We can also think of when we put salt into water. We know from learning about solubility that sodium chloride is going to break apart. It's soluble. And that process of breaking the ionic bond is endothermic. So, will salt water make the water cooler? It might. That'd be a good thing to check out on your own. Okay, so when we're talking about energy, there's units that we use. The international system, the international unit, the standard unit is a joule. Not like sparkly diamonds, but it's joule, Joule. It's a capital J. It's a great unit. So it's a joule, it's J. It's a unit of energy. Heat and work, energy in transit, are also measured in joules. A kilojoule is 10 to the 3 joules, or 1,000 joules. Now, we can also talk about energy in calories. You guys know what calories are. You've seen them on the back of food packages. You know that food contains calories. Well, what does that mean? 1 calorie is the energy needed to raise the temperature of 1 gram of water by 1 degree Kelvin. What does that mean? Well, 1 calorie is 4.184 joules. A calorie literally means it's how much energy that food is going to give you. The more calories, the more energy. It also means the more energy you're going to need to do, like burpees or running, to burn off those calories. Okay, so we've talked about systems and surroundings and energy and collisions, but now we're getting into real thermochemistry. We're going to talk about enthalpy. What? Enthalpy is, we're just talking about energy. Where is it going? Where is it flowing? So internal energy is the total energy contained in a system. It's inside. It's internal. It's in the system. And the change in enthalpy is the heat absorbed or released by a reaction at a constant pressure. And the change in enthalpy is designated by this little symbol. It's delta H. Delta means the change of, and H stands for enthalpy. It's from like an old word meaning heat. Which makes sense, heat. That's what we're talking about, the flow of heat. So we can talk about the change in internal energy. Energy gained or lost that doesn't involve a push or pull is heat energy. Energy gained or lost through pushing or pulling is called work. Heat can be gained from the surroundings, like the sun. So picture this. You are lounging on the grass on a hot day sipping some lemonade. And your brother is mowing the lawn. So you are losing heat through breathing and sweating in that lounge chair. And your brother, he's using energy in the form of work to push that lawnmower. Now, maybe on the table you also have a sandwich. Food is also an energy input. If you eat a sandwich, you can gain some energy because it has calories, which we learned have joules, which is energy. The change in internal energy is the sum of the heat absorbed and any work done on the system minus the sum of heat released and any work done by the system. Many reactions occur in systems at a constant pressure, such as a beaker at atmospheric pressure. To account for heat flow in such systems, chemists use a quantity called enthalpy. So similar to a beaker, an open pitcher of cold lemonade is a system at constant pressure, right? It's not a balloon, there's no pressure here, it's open because there's no lid. It's an open pitcher of lemonade. Enthalpy is used to quantify the heat flow into or out of a system or chemical reaction in a process that occurs at constant pressure. It comes from the Greek word meaning the heat inside. So let's look at these two pictures. In the picture on the left, we're starting with hydrogen gas and oxygen gas. And those two molecules are going to collide and react to form water. Now, this is an exothermic process. Heat is given off by the system to the surroundings. Now, if we flip this around and we do a different equation, we can look at mercury plus oxygen gas. Now, for the second one on the left, we want to start where the arrow is. So in this one, we have to put energy into the system. So heat is absorbed by the system. So we have mercury oxide. And in order to break that bond, we have to put energy into the system. So the energy goes up. The energy is flowing from the surroundings into the system. So it's making the reaction feel cool because there's less heat in the surroundings because now it's in the system. So it feels cool. It's endothermic. So enthalpy, the change in enthalpy equals the enthalpy of the products minus the enthalpy of the reactants. It's not that hard. You can do it. So delta H is the heat given off or absorbed during a reaction at a constant pressure. We're not really going to worry about if the pressure changes, okay? That's not what we're doing here. That's harder. We don't care about that. Now, if the enthalpy of the products is less than the enthalpy of the reactants, and the total enthalpy is less than 0, we're going to have delta H is negative. And that's an exothermic reaction. So if delta H is negative, it's exothermic. Now, if the enthalpy of the product is greater than the enthalpy of the reactants, and the enthalpy is greater than 0, then delta H is positive, and it's going to be endothermic. So we can look at these pictures again. Okay, so is delta H negative or positive? So we can look here and we can see that the energy is flowing up, right? And here, delta H is positive. Heat is absorbed by the system from the surroundings. So we're putting energy into the system. We have solid water, ice, and we're melting it. In order to melt ice, it's going to require energy. Ice just isn't going to melt itself. So delta H is positive, which means the system is absorbing heat, and it's endothermic. and delta H is greater than 0. In fact, it's 6.01 kilojoules. 6.01 kilojoules are absorbed for every 1 mole of ice that melts at 0 degrees Celsius and 1 atmosphere, which is a unit of pressure. And it's the standard pressure. So when we melt ice, it's going to require energy. So the process is endothermic. Now, let's look at this other one. Look at the arrow to see where the heat is flowing. This arrow is going down. We're going from methane, CH4, plus oxygen gas. So when we combine methane and oxygen gas, oh, look, we have a hydrocarbon and it's reacting with oxygen gas. I wonder what the products are going to be. Oh yeah, it's combustion, so our products are definitely going to be CO2 and water. So in this case, this is combustion. And we can see here that our delta H is negative. It's negative 890.4 kilojoules. This system gives off heat. We're burning stuff up, okay? In fact, this is like lighting a fart on fire. We have methane and oxygen. It's going to produce some heat. It's exothermic. The heat is flowing from the system to the surroundings. Delta H is way less than 0. 890.4 kilojoules are released for every 1 mole of methane that is combusted at 25 degrees Celsius and 1 atmosphere. 25 degrees Celsius is like normal room temperature. It's probably how warm your house is right now. Okay, so bond enthalpy. I want to remind you that bond formation is always exothermic, and bond breaking is always endothermic, regardless of the value of delta H. Every enthalpy diagram for a reaction starts by adding energy to break bonds and then ends with releasing energy by forming new bonds. So bond enthalpy is the amount of energy needed to break bonds of 1 mole of a substance. And an enthalpy diagram, which I'm going to show you in a second, is a representation of the relative enthalpy of a system undergoing a chemical change. Know this forever, tattoo it on your arm, never forget it. Energy is absorbed from the surroundings when a bond is broken. Okay? If you're gonna break a bond, think of a pencil. Like, put a pencil in your hand. Now break it. If you're breaking that bond, you're putting energy into the system. It's coming from the surroundings, you, going into the system, into the pencil. It takes energy to break a bond. And energy is released to the surroundings when a bond is formed. When energy is released, feel it as heat, it's hot. Okay, so let's take a look at this enthalpy diagram. We're going to start on the left, and as we see, enthalpy, if we look at the y-axis, it's enthalpy, and the y-axis goes up. So we start with the reactant molecules. We have 3 different molecules, or we have 2 different molecules. We have 2 of the same molecule. And the first thing we're going to do is an endothermic process of bonds breaking. We're going to break those guys up. We're breaking them up. If we're going to break up molecules, it's going to take energy. That's why we're going up. We're going up. Enthalpy is going up. It's taking energy. Now, we have these molecules and just colliding around each other, and they're going to rearrange themselves. When those molecules rearrange themselves, that process is exothermic. We're making bonds. When we make bonds, the energy is not going into the system. It's going out to the surroundings, and we're going to feel it as heat. So that process doesn't require energy. It releases energy. Now, do you see the energy that we started with is different than the energy that we ended up with? Do you see that? It took less energy to break those bonds. Let me rephrase that. So as we see, we go lower. Our enthalpy is less than what we started out with, right? So overall, this reaction is exothermic because we fell lower on the enthalpy scale overall. So delta H for this reaction is exothermic. Okay. We can also look at bond enthalpies on a table. So the average bond enthalpies for some bonds are listed on this table. There's more extensive tables of average bond enthalpies, and they can be found online. Actual bond enthalpies they're going to vary depending on the overall molecule. Like, who else are they attached to? Because if we have polarity and something's really electronegative, it's going to pull on that bond and make that bond shorter or stronger. So this is an average. So this is a good estimate. So let's take a look at this. Let's start with a carbon-hydrogen bond. A carbon-hydrogen bond, if you want to break that up, you want to break them up, they're over, they're done, the relationship's gone. If you want to do that, it's going to take some energy. It's going to take 413 kilojoules to break them up. Now let's see, some are less, some are more. Why? It just depends. We can look at, maybe we can go through the halogens. That's kind of fun, right? Okay, so we have carbon, hydrogen, that's 413. Now what if we have, let's go to the halogens. So if we have chlorine and fluorine, that's 485. That's a lot. That's a strong bond. Now let's look at carbon and chlorine. That's 328, it's less. Chlorine and bromine, 276, less. Chlorine iodine, 240, even less. That's because fluorine is super electronegative and it really doesn't want to break up that bond. So it's going to take a lot of energy to take those electrons away from fluorine because it does not want to give them up. Now let's look at something else. So we looked at carbon and hydrogen is 413. Now I want you to look at the multiple bonds. Look at that carbon-carbon double bond. What do you notice? What do you notice about the single bonds versus the double bonds? What do you notice about their enthalpy? I'll give you a second. It's like Dora the Explorer. Yeah, it's greater. Good job. You got this. Now let's look at those triple bonds. Look at that carbon-carbon triple bond. What do you notice about that? Yeah, you're so smart. It's even greater. 839, that's a lot. That's pretty huge, right? It takes a lot of energy to break those multiple bonds. Okay, we're almost done here. So you are almost done. Using bond enthalpy to estimate reaction enthalpy. We can do this. Enthalpy of reaction. Since energy in reactions comes from breaking and forming of bonds, you can use the average bond enthalpies to estimate the total change in energy for a reaction. So what we're going to do is we're going to take our enthalpy diagram and we're going to combine it with that enthalpy table. We're just going to combine them now. You can do it. It's okay. We're adding and subtracting. You got this. Just remember, during a chemical reaction, bonds are broken and they're reformed in different ways. We're breaking them and we're mixing them up. So take a look at this. We're combining our enthalpy diagram with our enthalpy table. So here we have water. We have 2 moles of water, 2 molecules of water. And if we looked at our enthalpy diagram, we can see that water includes, each molecule of water includes 2 oxygen-hydrogen bonds, right? So we have that oxygen-hydrogen bond here, and we also have one here. And since we have 2 molecules, overall that's 4. So we're going to multiply the enthalpy of breaking that one bond by 4 because we have 4 bonds. Okay? So that's what we're starting with, because we know when we're forming a reaction, we're doing a reaction, first we got to break it, mix it up, and then we make it. We make some new things. So the average bond enthalpies can be used to estimate the change in enthalpy for the overall reaction. The reactants have 4 oxygen-hydrogen bonds, and those all have to be broken. So when we break bonds, it takes energy. We're putting energy from the surroundings into the system, and that process is going to be endothermic. Okay? Now, if we see this, we see if we multiply 4 times 467, we're going to get 1,868. So it's going to take 1,868 kilojoules of energy to break those bonds. Now, what we get when we rearrange, the products have 2 hydrogen-hydrogen bonds and 1 oxygen-oxygen double bond that's going to form. Now we know when we form bonds, that process is going to happen, right? We're not adding energy. Energy is released, right? Energy is released into the system. It's an exothermic process. So we're going to flip that enthalpy sign because the energy is released. So we have 2 hydrogen-hydrogen bonds, which are 432 kilojoules, and we're going to add that to that 1 oxygen-oxygen double bond, which is 498. So altogether, it's 1,362 kilojoules. But this isn't required. This is released. So we put a negative sign because exothermic processes have a negative delta H. Now, what is the overall? Well, the overall enthalpy of this reaction is 506 kilojoules. That's a positive sign. So what does that mean? That means that overall, this reaction is endothermic. And it makes sense because look, the energy we started with is less than the energy in the product side. That means we have to put energy into the system. We put energy into the system, it's endothermic. And we're going to feel some cooling off when that happens. Okay, guys. Thank you so much for hanging tight and listening. After this, you are good to go on the warm-ups, and that's what you need to do in order to showcase your understanding from this lecture. Thank you.